So I want to get like a little bit like a 10,000 feet view of what we are doing. And I think like a lot of like people, when they start to use Copper or start to look at the architecture of Copper, I think they don't understand what we are really trying to solve. And I want that presentation to be about this, like a little bit, taking a little bit more time that I usually do in presentations in like I don't know, conferences and so on, to really deep dive into, okay, what in me pushed me to actually create this new type of kind of operating system. And it's so funny. So I'm talking a lot of people interested by Copper and so on, and often my question is like, where is my robot? Like, you see like a lot of videos for like almost like 2 decades, and of like robots everywhere, robots dancing, robots doing a lot of things. You see the progress in AI everywhere also. There are, I don't know, there are folding robots and so on, but honestly, the only robot you can really touch today that's gonna be fully autonomous and safe, that will be Waymo. And that's it. Those Waymos are billions of dollars in the red. You have to realize that. And I'm pretty sure every single ride today, they are not even recovering money. So it will be a long time, probably again a decade before they start to actually get money compared to, let's say, putting people in that car and actually drive it. So that's where we are in terms of autonomy today, and that's the best we can see. Of course, you have like, yeah, those demos like where you have like a robot dancing and doing kung fu and so on, but I don't see them. And you have those things too, right? Oh yeah, we will have like air deliveries pretty soon. Amazon did that, and so on. So yeah, it looks like, yeah, it's not a solved problem today. So you have a lot of things in the lab, for sure, very successful projects, very successful like academic projects too, but as a product, not many. I mean, you can buy this robot, but yeah, guess what? It's better to you see the little things that are actually hanging on the shoulder of that robot. Yeah, you better put that, because like they can get insane. I don't know if you know this video, but yeah, those robots are yeah, when they are very like in the let's say in the happy path of what they are doing, they are incredible. But once they actually get unstable or not in their like kind of operating domain, they can be very dangerous. So those robots can go easily through like a drywall. And yeah, same thing for the air deliveries. That's wing. You know what? I'm pretty sure that no one in the airspace have any kind of like detection system or sensing system that actually detect like power lines. They just do that like with like automation instead of autonomy. And yeah, when they get stuck in a power line, they don't even realize they are stuck in a power line. I'm pretty sure those robots. And yeah, so we are stuck with this like a stupid Roomba that gets your gets your toilet paper and put that everywhere in your home. So why is that? Why is it so difficult to actually get something that works very well in the lab and kind of start a company, roll with it, iterate, and make like a successful autonomous product? You have it's an open environment for autonomy. You have to realize that if you are near people, near pets, on the public roads, in the air, yeah, there will be like a bunch of cases that are very common. Like you will see, I don't know, let's say you are doing like self-driving trucks, you are on a highway, you will have like millions of miles of like straight empty highways in front of you. Cool. Same thing, like you are in the air, it's going to be, oh, there is nothing in the air, there is no power lines and so on, or you are on an AMR and yeah, you have no bumps, no nothing. The thing actually works. And usually this is very early on, and that's where you can actually already send videos to investors for your company, for example, or your project in academia. But then it starts to get a little bit complex. more complex. So yeah, on the x-axis, sorry, I'm just over the thing. Maybe yep. That's a dev timeline. So as you actually going along your development, it's get harder and harder to get those cases, and those cases are and more rare. So think about it. It means that your data, as you are going along and trying to get those cases that are a little bit like more less like common, this data is going to be a little bit more expensive to get, right, from either like a simulator or the real world. But then there are those cases, and what we call the long tail in the autonomy space, where, yeah, you will have more and more rarer and rarer events that you need to actually cover your operational design domain. If you miss those points, you are not safe. Basically, you don't know. You never tested something that is actually at the edge of your operational domain, and that's a huge issue. Like that's how you get those robots that goes like crazy and so on, because yeah, they are basically a point somewhere there maybe that you never encountered yet, you never fixed, you could never reproduce, and you might have this issue with the customer in front of it. So yeah, this exercise is all about trying to cover that operational design domain with as many cases as possible and as densely as possible, to say someday, hey, you know what, I covered it and it's safe to use in that domain. And the path to success for this is to go from this green side to that red side as fast as possible, where it cuts, where you decide, yeah, you know what, after that it's so rare that I don't really care, then you can move on and actually deliver your product. And that's where the kind of like the first principle design we came up with Copper is determinism. Because what we want to be able to do is like whatever happened in one case live in your robot or in the simulator, like ideally you have the simulator and the live things that are as close as possible. So now we start to have like good simulators. We want those guys to be as close as what you can actually test from the data you captured from your data set. Okay, so physically, what does it mean? It means that, okay, you capture some logs, either live or from a simulator. You strip the outputs. You leave only the inputs. You re-simulate it. So basically, you take that case and you replay it. And you have 100% of your outputs that match your outputs that were actually happening on your robot. That's a very important thing. And we do actually, thanks Young, I see Young in the audience, thanks Young, because now we have a deterministic test on CI that does that every time we commit something to Copper, because it's very easy to break. Like you can add like some randomness in the stack, and you have this mismatch. But we have one that is hard. Like literally, you compare that file with that file, and that's what we do. And byte by byte, they are exactly the same. You have a strong guarantee of determinism. The second one that is very important for those robots that will become products, or like for advanced, let's say, academic work, is performance. So why? Usually when you want to build a robot, or any software, when you think about it, you want to be able to have modules that are as small as possible. Why? You want to decompose your problem. Even if you have an end-to-end like machine learning algorithm, you will have a lot of things like we are like in self-driving cars, like 200 of those boxes, like because you have a bunch of cameras and sensors and actuators and like safety monitors, and like you can imagine like an entire thing, like how do you open the doors and so on and so on. So even if it is an algorithm end-to-end, you will need something that actually is pretty well decomposed, where you can actually see what's going on between those tasks. The problem is like, especially with ROS, with the performance that sucks, people tend to, you know what? it's so expensive to get those little like capture points between your tasks that you end up with something like that. And I've seen that so many times in so many companies. Basically, they bunch up all their logic into one big task, and they have, oh yeah, maybe some sensing there, some actuation, and they bundle like a bunch there also, because it's like so latent and so unpredictable at every single intersection there, that they prefer to actually minimize the risk and actually have that like as small as possible. That sucks, right? You lose visibility, you lose composition, you lose as like a community for us, you lose like reuse of small components that are readily available in the community. Because yeah, the bigger it is, the less useful it is, because it's going to be like so tied to your own use case and not tied to the use case of everyone. So Copper, what we want to do is to be so performant that all those points are basically free. So people don't even think about it. They will decompose that. And as a community as a whole, it's going to be interesting to see like a lot of like micro components that compose one another, that gives a lot of visibility, that logs in between, that you can look at in terms of like introspection in the system, in the logs and so on. And that also gives you a way to actually pinpoint things like very easily. Like when you are in the debug mode, for example, you will have all this data like logged, and you can make a condition on that piece of data and get it like right away, instead of like waiting for like this thing trying to reproduce it. Maybe yes, maybe not. Put a breakpoint in the middle of your big task. Now, when you talk about performance, there is something that is kind of like hard. One is on the left-hand side. I think that's left-hand side for you, hopefully. you have like modern computer architectures. They are huge parallel machines today. They are like multi-core, lot of caches, like non-uniform memory, like a lot of like buses and various speeds and so on. That makes that computer really, really complex. And when you look at those computers, they are not made for robots. They are definitely not made for robots. Your processor on your laptop or your desktop, they are made for bandwidth. They are made to do what I'm doing right now, streaming video with like a bunch of things going on at the same time, and you don't really care. It skips a little, but okay, you have a bunch of things running at the same time, and this thing tries to optimize like that runtime as much as it can, but it's really like best effort. So you have this very opinionated thing that if you go well with it, it goes fast, but if not, it can actually trash a lot. It's really narrow what it can do. And on the right-hand side, when you think about algorithms and when you talk about people like you, roboticists, usually this is not a world they even encounter in their like professional life. It's just like, yeah, I want my algorithm to work. I want my math to work, my transforms, my I don't know, my computations on my in kind of a graph that you can abstract with input output. So it's easy for me to see like a pure function out of my little function I want to do on my robot. But that's it, right? Like they usually don't care about like, is it parallelizable or is it like, can we do like SIMD on top of it and so on? Usually it's not a concern. They prefer to think about like the problem is already hard to solve. They don't really think about the left-hand side. And in terms of like, let's say, trade-offs. So you've seen, we want determinism, we want performance. The computer is actually complicated. You have a lot of things that goes against one another. For example, you have like what we just talked about. The low latency is actually fighting the bandwidth. A computer, either you actually optimize it for low latency. Actually, in the 80s, the computers were pretty fast in terms of latency, or you optimize them in terms of bandwidth. And you know what? It's way easier to optimize the bandwidth side than the latency side. Why? Because you can always like add cores. The silicon now, it's like the space on the silicon is pretty cheap. So yeah, you can always add caches, add cores, and so on. And all those things goes toward bandwidth, not really latency. We talked about this one, the real world versus math. Like that, those are kind of like, the more abstract you are, the harder it's actually to fit in the real world, and the more leakage from the real world you have into your math, the harder it's going to be for you to reason about your algorithm. That's also kind of a tug of war when you think about like, the design of something like Copper. Safety and ease of use. Yeah, usually safety is about like making things very static. You don't change stuff. Ease of use and experimentation, for example, is all about like, yeah, I can change stuff like all the time. They are also like in kind of a tug of war when you are deciding where you want to put your SDK in. The last one I have is the AI performance versus cost, which is also an important thing. So AI performance is really costly in terms of like silicon and so on. So yeah, you want like your as smart as possible robot, but you don't want to actually blow up the price of the computer. You will put all the power you will put in your robot. So all those are things where we have to look at what existed and how we can kind of go towards more like a product for Copper, but also not sacrificing too much of the other side. You see, if we are like only low latency, we are in trouble, because suddenly you will have images and you need bandwidth. If you are all AI performance, it's going to actually cost too much in terms of BOM cost, and so on and so on. So there is like this design trade-off we need to navigate. So that's kind of like putting that all together, like the few previous slides I talked about. So we need to have something that, like, whatever happened in the robot has to be captured and be reproducible, deterministically reproducible. Another second part about performance, the rule number one of performance is do not do it. If you don't do it, your thing is instant. And that's the mistake of the other frameworks, Dora, ROS, like you name it. You look at them and you understand that, like, oh, why ROS is starting in a SQLite database. Yeah, because the robot indexes this database. Why? This index is not for the robot, it is for the human. So everything you can do, index outside of your robot, pre-compile stuff before your robot, I don't know, give priors to the world for your robot, you do it. Because, like, again, if it is not happening on your robot, it is free. We talked about like the throughput and latency. Latency is actually the more critical part, because what I said, computers are made for throughput, bandwidth, and once you don't, I don't know, pet them just like you need them to, the first thing that goes out of the window is latency. And we talked about like the API. It needs to be safe like in the two meanings of the term, like in terms of like computer safe, like memory safe as term of safety, and they need to be able to be used for people that do basically physics and math. So in terms of like, okay, now we are rolling back to Copper. That explains those three things. Basically, Copper is a compiler. Why? Because we need to be able to do stuff before we push it to the robot, so the robot doesn't have to do it. Okay? That's why it's a compiler. It's technically a compiler. It's also an operating system. Why? Because computer architectures are very complicated, and if you rely on another operating system, that will shoehorn basically the output of Copper toward those like bandwidth biased type of buffering type of things, virtual memory and so on. That's gonna be really hard for Copper to deal with. So of course you can get like a real-time operating system, but with Copper as like as a task that works not bad, but basically you are trying to shortcut those layers of operating systems, because they are noise and usually are not optimized for what you want to do. And we want a safe compute graph. That's what we mentioned before. We want something where people can play with, have components, and switch components, monitor the inputs and outputs. And yeah, this is why Copper is a gigantic proc macro. That's why also Copper can run on bare metal. And that's also why Copper has been designed to run in Rust. A lot of people are actually asking me why don't you put like the Python APIs? You start to understand why. Because once you have like one line of Python in your code base, everything we talked about actually goes out of the window. So that's why Rust is one of the pillars of Copper in terms of like, how do we make something fast, deterministic, and that we can actually generate at compile time instead of having the robot trying to figure it out like Python. Like Python is literally compiled on the robot in real time. All right, we're almost at the end. So let's go into, how did we implement that at the end of the day? So some people know this, but probably some people don't. And so let's go through this, right? I call that like a data-oriented, deterministic, metamorphic operating system. Oh, that's a mouthful, but you get it. Data-oriented means that we will organize the memory. So when we execute through the tasks, we will hit the caches, prefetches, all those things that are bandwidth oriented on those target computers that will love that, right? Like they love to be able to do stuff linearly or already cached. Deterministic, we talked about it. We have the input outputs that match the replays. Metamorphic means like basically we do that depending on what you ask it to do. So basically on your graph of tasks, Copper will basically generate an operating system just for that graph. You add a task, it's going to be a different operating system, a different scheduler, a different way of actually running it. So it's very static, an operating system, because we said like, we need to touch the bare metal up to those algorithms. So concretely, how it works, you give it your DAG in your config, and Copper at compile time will generate two lists. One is basically the list of your tasks in order of execution. Here, for example, you might say, it's going to be task 1 that executes, and task 3 that execute next, right next in memory. Then 2, it's going to be there, so out of the output of task 1, and then task 4 at the end. And what we will do in terms of like, how do we represent those like kind of messages going from one task to the other? It's going to be a list ordered in memory in the same order. So it's pretty powerful. So imagine you are on task 1, it will write in that piece of memory. When we'll go to task 3, it will go to the next piece of memory on that memory channel. On that memory channel, it will reuse the same thing that is already cached and probably super close to the CPU. Then you go to task 2. Guess what? Boom! You are hitting again the same one, exactly after the previous one, so you have less chance to have that like evicted from the caches. And then you go task 3, that's going to generate an output there, right the next bytes, so it's going to be again hitting the pages, caches, prefetching everything you have in your computer, and then execute there again, prefetched already in the code caching, because it's a task literally that is beside it. So, and that is going to be run twice. Once is like the real-time execution. The goal of it is to be from sensing to actuation as fast as possible. So that red thing is just doing thing in memory back to back. And then the second time, at the end, we need to be able to log it. But it's going to be between cycles. So we can have some parallelism. We can actually start to dump that to disk while we go into the next cycle. And tasks, same thing. It's going to be linear, boom, back to back. And from time to time, very rarely, we take it's more like a safety, because like logs can be long. We log like a keyframe. That's why you need to be able to serialize your own tasks. And that's pretty cool, because it serializes the internal state of those tasks. So when you debug, for example, the application, you can actually come back to those keyframes directly out of a log. So that's something we do because, like, yeah, logs could be corrupted, and even if it is deterministic, if you lost the beginning of the log, so then the end of the log is actually hard to catch up on. So those keyframes can reset basically the determinism to be sure at those keyframes. So yeah, that's it for this first presentation. I'd like to switch to questions basically, and go to you guys, like saying like, yeah, how much did you learn first from that presentation? I'm curious, and if you have like thoughts about it, thoughts about like determinism. Is it like a problem in your space? Do you have like use cases where you hit that, and also performance and like basically almost like all the constraints, the design constraints, like when we did that tug of war, did you felt it using Copper, or is there like a thing we should adjust on those things? So anybody would love to go through questions? The one I see everybody that is like that is muted. No, timid people. All right. Yeah. Oh, sorry, I cannot hear you.
Hello, can you hear me?
Yeah, I can hear you.
Yeah, sorry, I'm driving, so maybe help me here. Thanks a lot for the presentation. I wanted to know if you could give more details on the logging, how to replay the post.
Oh, sorry, I could not hear you. Do you mind like typing the question, like in general or something?
I typed in the chat, please.
Anybody else while we are waiting for the question? Sorry, Nico, your audio was so choppy that I could not understand. I don't know if it is on my side or on your side, but it was really
Yeah,
choppy.
sorry, I typed in the chat.
Ah, okay. Oh, where? Do we have a chat? Oh yeah, I see. Okay. Can you give more details on how to replay the log once we have them? Oh, good question. So we do have, so like as usual in Copper, so the big trade-off also in terms of usability is that I did not want to give executables to everyone. Why? Because usually your workflow might be different. You might want to replay that in a simulator or replay that in something else. So I encourage you to look at the examples, and we have like basically a call you can make to the Copper runtime. You basically switch it to sim, and you can actually inject like your data from a log. You have like a bunch of examples. You can do that like with for example, the balance bot as one you can replay, and you give it like an input log, an output log, and it will re-execute your log and re-executing it from inputs to outputs. Basically it does the same thing as what it does in simulation. You know when you have this virtual environment, it basically injects data in your DAG. It will do the same thing, and it will execute actually Copper that will want to, okay, where do I log my output, and you can actually rebuild an output out of it. So yeah, that's how you do it. Like go to the examples, and we have like several ones. I think also the one with the Caterpillar also has it and so on. So just take the two, like another few like a dozen line of code that you have around your those like main.rs, and you can do that. And you can check after that. There is also a cool feature that we can enable on those regimes is the debug API. So it's super powerful. Basically, you can take your log, stop the world for Copper, and be able to actually go in time, like left and right, and grab the state of any tasks at any time, like step of Copper, and any messages, and grab them through this API that has like can give you like also the schema, for example. What are those fields from that task? What the ID of that task? What are those fields for this message and so on? So it's super powerful, and we want to, on that with simulator, right, be able to debug very easily Copper.
Okay, thank you. Thanks a lot.
Cool. Any other questions?